Hi, this brief video is on ordinal regression. Unlike in logistic regression, where we only have two categorical responses for the dependent variable, in ordinal regression, the dependent variable can have three or more categories, and we're going to further assume that those categories can be unambiguously put in a specific order, or more specifically, we don't have nominal data. The idea behind the regression model is that as one or more of the independent variables increases or changes, it would result in a shift toward either end of the spectrum of the ordinal response or the dependent variable. Said another way, the probability of responding toward either end of the spectrum, for example, the positive end of the spectrum, would increase as the predictor variables change in any given direction. Let's say that we have J-ordered categories. So for example, if we're looking at the standard 7-point Likert type response scale, which ranges from strongly disagree to strongly agree, we would have J equals 7 categories. In particular, strongly disagree, disagree, slightly disagree, neutral, slightly agree, agree, and strongly agree. What we're going to look at next is two but very related models for ordinal regression. The first is called ordinal probit regression, and the second is called ordinal logistic regression. To introduce probit regression, we need to set the stage by introducing the concept of the latent variable. What we're going to imagine is that we have this variable y star that we can't see, and because we can't see it, we can assume a lot of interesting things about it. For example, we can assume that it follows a normal distribution. The idea of the latent variable is that as you respond more highly on the latent variable, you're more likely to respond higher on the ordinal scale. What you can see here is that we've added breakpoints, or what are called tau cuts. These tau cuts separate up the normal curve into regions in which people would respond in a certain way. So for example, if someone had a score of 2 on the latent variable, then they would respond strongly agree. Let's use a context here. Let's say we're asking if people like chocolate ice cream. If someone had a score of 2, then they would respond that they strongly agree that they like chocolate ice cream. However, if someone had a score of 0 on the latent variable, then they would indicate that they agree that they like chocolate ice cream. Whereas if someone had a score of -3 on the latent variable, they would be in the farthest region at the bottom of the spectrum, and they would indicate that they strongly disagree with the statement that they like chocolate ice cream. For this particular picture that I've drawn here, I've put the tau cuts specifically at the values indicated, from -2.1, -1.5, -0.6, and 0.7. If someone had a latent variable response between -1.5 and -0.6, then they would indicate that they're neutral with regards to the statement, I like chocolate ice cream. Here we can see each of the regions of the bell curve shaded, and the amount of the shaded area indicates the proportion of people that we believe would respond in each of the categories. More specifically, we can see that with these particular tau cuts, we would predict that about 24.2% of the people being measured would respond strongly agree, whereas only 1.8% of the people would indicate that they strongly disagree with the statement. We could also re-represent this as a stacked pie chart, if you wish, in which case we can see the proportion of the people responding on the different levels of the ordinal scale, where the dark red indicates the proportion responding strongly disagree, and the green indicates the proportion indicating strongly agree, and the values in between are scaled proportionally. This gives us an idea of how we can map responses that follow a normal distribution into a set of categories that are ordered in the same direction as that normally distributed variable. To understand how to interpret the output from an ordinal probit regression, we'll use the following scenario. This is a data set that was found online. I believe it's just a toy data set or a simulated data set to help with the demonstration. But the context is as follows. 400 people were asked if they intended to go to grad school, and they were given 3 response options, ordered from unlikely to somewhat likely to very likely. Along with collecting the information on this response, they were also asked to report if at least one of their parents had attended graduate school, if they had attended a public or private university, and their GPA that they earned while at school. So that's the scenario that we're looking at. Here's the output that was obtained. So this is the ordinal probit regression output obtained from R using the 3 predictor variables to predict the ordinal variable. What we're going to notice is that the output has 2 parts, and we're going to talk about this shortly. There's the part referring to the coefficients and the part referring to the intercepts. And we're going to analyze each of these in turn. We noticed that the output had 2 parts. The first was the formula to calculate each person's latent score, the y star, and the second part was the position of the tau cuts. Those are the values against which we will compare the y star to determine into which category each person falls. Again, looking at the first part of the output, the coefficients are reported, a value for each of the 3 independent variables that were in the model. Taking these numbers, we can create the following formula to predict the latent variable score. You can verify by plugging in the particular values given here, but a student with a GPA of 3.3, whose parents did not have an advanced degree, and who went to a private school, would have a y star of 1.18. Alternatively, a student who had a GPA of 2.9, who had at least one parent who earned an advanced degree and who went to a private school, would have a y star, or a latent value, of 1.64. However, these values can only be interpreted in comparison to the tau cuts. So the second part of the output that we need to attend to is the positioning of the tau cuts. Returning to the output, the part of the output that we want to attend to is the intercepts, in which it gives the boundary values between the different categories. We see the first category separator is between unlikely and somewhat likely, with the value of 1.2968, and the next tau cut separates the next 2 categories, somewhat likely and very likely, at the value of 2.5 and change. Here we have the information summarized. Again, the separator between unlikely is at 1.297, the separator at very likely is 2.503, and in between those 2 tau cuts is the range in which we would find someone that is somewhat likely. To help clarify this a little further, we can specify the regions in which people would be predicted to report whether or not they were unlikely to go to grad school, somewhat likely, or very likely. Someone who had a y star value of less than 1.297 would be predicted to respond that they were unlikely to go to grad school. So that would be the prediction for our first student, the student with a GPA of 3.3. The next range is between 1.297 and 2.503. Any latent variable scores appearing in that range would result in the prediction that that person would respond that they're somewhat likely to go to grad school. So that would be the prediction for our second student, the student who had a GPA of 2.9. And lastly, anyone who had a latent variable score of 2.503 or larger would be predicted to respond that they are very likely to go to grad school. Next, we want to look at what happens to the predicted values as the independent variables change. To help us visualize this, we can look at an animation that shows what happens to the probability to each response category as the GPA changes. The key to note here is that as the GPA changes, the latent variable score y star also changes. In particular, as GPA increases, the latent variable y star increases. We can see here an animation that shows what happens as the GPA decreases and then begins to increase. What we notice is that the predicted value, the center of the bell curve, moves from the very likely region to the somewhat likely region to the unlikely region. In particular, as the center of the bell curve moves, the values for the probabilities shift accordingly. As GPA decreases, we notice that the probability of responding unlikely to going to grad school increases, whereas GPA increases, we see the probability of responding very likely increases. Now let's carefully examine the predicted probabilities for one person. So we'll take a third student. This student has at least one parent with an advanced degree, they attended a private school, and they had a GPA of 3.21. Using the formula, we can see that their predicted y star value would be 1.748. This will become the center of the standard normal curve for this student. Here we see the results for the student. The standard normal curve is indeed centered at 1.748, and the tau cuts remain in the same position of 1.297 and 2.503. This person's predicted y star ends up in the somewhat region, but what we see is we can calculate the probability of this person responding somewhat, and that turns out to be the area under the curve from 1.297 to 2.503 when the curve is actually centered at 1.748. The probability turns out to be about 44.9%. However, we see that the area under the curve below 1.297 turns out to be about 32.6%. And lastly, there's still a non-negligible probability that this student would respond very likely to their intentions to go to grad school, with an estimated probability of about 22.5%. So while the y star does indeed give us the predicted value to estimate how a person might respond on the ordinal scale, the truth is the model provides probability estimates for how they would respond in each of the categories. The next thing we'll look at is the second type of model estimation, which is the logit regression. Now we'll look at ordinal logistic regression. Ordinal logistic regression builds off of the idea behind binary logistic regression, and that is the idea that you take your probability, transform it to an odds, take the log of that value, and then you can conduct regression on that transformed value. However, to do so for ordinal regression requires thinking about cumulative probabilities instead of individual category probabilities. When you only have two categories, if you predict the probability for one of the categories, you automatically know the resulting probability for the other category. In ordinal regression, we have to assume that you make it up to one particular category, and then you know the probability of being in that category or having been in a category larger. This is why the technique requires the dependent variable to be an ordinal variable, as you can talk about cumulative probabilities of obtaining at least a given category only if it's possible to put the categories in a given order. Before we look at the output, let's take a look at some of the necessary mathematics behind the analysis. The first thing to note is that we're going to be talking about the cumulative probability. So assuming we've taken our ordinal dependent variable and just labeled it from 1 through j because there are j categories, we can ask what's the probability of getting up to category 2 or category 4 in that ordering. We're going to define the cumulative probability, f sub j, as the probability of the output being at least the value j, given the dependent variables that we're looking at. Now, with that probability, we can transform it to the odds, and then take the log of that to transform it to the logit, and that would give us the log of the probability of being in category j or less, 1 minus that probability in the denominator. The log of that value gives us the logit. Using this information, we can now run the multiple regression model, but in this case there's actually going to be j minus 1 equations in total, because we're predicting the cumulative probability for making each transition step. Of course, we don't need to calculate the probability for the last category because the probability of being in the highest category or any below it would be 1, and there's no need to calculate that. That's why in the end there's only going to be j minus 1 equations. However, there is something important to note here, and that is that we are actually subtracting the model estimate values that we obtain. The reason for that is best explored by thinking about the fact that when we were doing ordinal probit regression, we had to plot the normal curve, and then we were looking at the values compared to the tau cuts. A similar idea takes place here. Another way to think about this is the fact that previously we were looking at categories of 0 and 1, and we were actually predicting the probability of finding the category 1 instead of the category 0. We've switched things around here, so the signs have to change accordingly. This is an important point to remember when you're looking at the output from the statistical software that you're using. Most software packages do report it the way it's going to be shown here in the R document, because it's easier to interpret the relationship between the independent variables and the relationship that you're going to see with the ordered categorical variables for the dependent variable. Now, all that being said, it's probably best to demonstrate this by walking through the output. So let's take a look at the output here. This is the output for an ordinal logistic regression using R. It looks very similar to the ordinal probit regression that we saw before, except we have to be careful because the coefficients and the intercepts are interpreted in a slightly different way. What we're going to see is we'll use the coefficients to calculate the estimates, and then we'll actually use the intercepts actually as intercepts for the different cumulative probability calculation estimates we have to calculate for this model. Taking the values from the output, we can plug in and generate our two equations. The first equation gives us the logit for the cumulative probability of reaching at least the unlikely category, and the second formula gives us the logit of the cumulative probability of reaching at least the somewhat category. The model estimate values is the same, and we're actually subtracting that from the different intercepts that we obtained from the output. We'll continue working with the sample student we were looking at before, which had at least one parent who had a graduate education, went to a private institution, and had a GPA of 3.21. Plugging in these values into the equations above, we get that the logit values are negative 0.82 and 1.27. Converting these logits to odds by exponentiating them, we see that the odds of being at least in the unlikely category is 0.44, and the odds of being in the somewhat category or less is 3.58. Transforming the odds back to probabilities, we get the probability of being in the unlikely category is 0.306, and the probability of being in the somewhat category or less is 0.782. One of the key things to remember with this output is that the resulting values give you the cumulative probabilities. So this is the probability of being in the unlikely category or less, in which case it's actually just the unlikely category because there's nothing below the unlikely category. But the second probability is the probability of being in the somewhat category or less, which means the probability of being in the somewhat or in the unlikely category. To get the probabilities for the individual categories, we need to do a little bit of arithmetic. So again, as we already mentioned, the probability of being in the unlikely category is the same as the cumulative for being in the unlikely category because it's the lowest category. At the other end of the spectrum, the probability of being in the very likely category is simply one less than the probability of the cumulative probability for the somewhat category, which would be 1 minus 0.782, or about 21.8%. To get the probability of being in the somewhat category, we recognize that if we subtract the cumulative probability of being in category 1 or less from the cumulative probability of being in category 2 or less, that would give us the remaining probability of being in category 2, which is 0.476. Now, with this information, we can actually compare the two probabilities that we'd obtained. Using ordinal logistic regression, we found the probability for our student of responding unlikely that they would go to grad school was 30.6% when using the ordinal logistic model, but using the ordinal probit model was 32.6%. You'll notice that these probabilities are all close to each other, but they're not exactly the same. And that's one of the important reasons why we can take advantage of the fact that the two models give slightly different estimates to help us better model the data that we've obtained with a model that most appropriately matches that data. I hope this little review was useful. Thank you for listening. Bye-bye.